So I'm going to start the recording now, and so okay. So we have kind of spoken on the concurrent computing, multi-threading so far, but today we will run through it and summarize a bit. Okay. Chinmay, can you access that link and open that presentation which I shared? So I'm going to stop presenting and you can present. Hello? Okay. So can Joel, is it possible for you to open up the presentation and kind of read through it? Okay, thanks, Joel. Oh, okay. So it's taking a lot of time, Joel. Okay, okay, switch. Oh, this is going to take time. Yeah, you continue switching on the laptop, no problem. Let me open it from my end. Yeah, I think you're echoing, so you have to be mute on either one of them or something. Okay, now you're fine. Yeah, there's a link that I shared in the chat. You need to open the presentation and read through it. Okay, okay. Yeah, so this is the link. Yeah, Joe. Yeah, it's come up. Yes. So you can maximize or something, a slideshow, view slideshow, and run through it. Okay, great. Yeah. So start reading this. Yeah, yeah. Yeah. No, no. Just go to the first slide. Yep. Rushing through the slides. Yeah. So start reading one by one. Okay, okay, hold on. Yeah. So can you go back? Yeah, you just hold on. I just want to, um, or maybe just go through it. Okay, no problem. Just read through it. So throughput computing is equal to. Okay. Yeah, go ahead. Next slide. Okay. Joel, your mic has a issue. I think it's breaking up for some reason. Constant. Yeah. Yeah. It's breaking up. Your mic has an issue. Okay. Yeah. Your network has an issue. Joel, it's okay. Can somebody else present? Can you go back? Can you go back? Yeah, can you go back one step? Yeah, yeah. So that is a mistake actually. It is not GPU, it is CPU and GPU is asymmetric multiprocessing, I mean asymmetric processing, because CPU is different architecture and GPU is different. So these two processes are asymmetric. Multi-core is nothing but your GPU, which is a symmetric multiprocessing. So the asymmetric means different. So it is CPU and GPU. Multi-core is GPU, which is symmetric. Okay, so that is a mistake. Yeah, go ahead now. Hello. Is your screen freezed or something? Hello. Hello. Can you hear me? Uh, Hello. I don't know. Hello. Hello. Okay, thank you, Joel. You can stop presenting and I will go ahead and present. Okay, so let's okay, so most of the stuff, in fact, almost everything we have, covered in the last lecture. But some terms that we came across, you must have heard about throughput computing. Okay, so what does throughput mean? So you can think of throughput as something which is like the number of tasks or the number of instructions. So a number of tasks that is executed uh, in a single clock cycle, for example. Or this could mean the number of instructions that is executed in a single clock cycle. Or this could mean the number of floating point operations per second in a single clock cycle. So this is so this measurement is usually called flops, and it is used to measure your GPU performance, which is your symmetric processor. Or it could just like we say number of instructions, so it can also mean number of million instructions per second. So this yeah, so hold on. Yeah, so this is called MIPS, million instructions per second. It is used to measure the CPU. Okay. The only thing that I wanted to cancel out is this. It's not single clock cycle, because in a single clock cycle, 1 second may have multiple clock cycles, right? Either you talk in terms of single clock cycle, or either you talk in terms of per second. If it is you're talking about per second, then one per second will have multiple clock cycles depending on the frequency of your computer. So either you talk in the per second terms, or either in terms of clock cycles. So this is how throughput computing basically means how many things you can do in a single go. So then that is what is throughput computing. So high throughput computing would mean what? High throughput means you can execute lot more tasks, or a lot more instructions, or a lot more flops, or a lot more million instructions per second. Something high throughput computing would mean something that you can do a lot more in a single go. So that is what is called HTC, high throughput computing. So when we want to achieve high throughput computing, so we look into multi-threading, right? We basically look at concurrent computing, right? Concurrent computing is like how can we do two tasks or two functions at the same time, and that is where when it comes at the program level, we use threads, right? So this is what this was a term which you saw in the presentation. And another thing that you saw in the presentation was if there is two processors, so one was master slave processor model, and another one was I don't know what it was called. Let me see. Uh, Hello. Okay, I am not able to find that slide where it is. So basically, the point is when you say it is a master-slave processor model, it means if there are two processors. So especially in a asymmetric uh, multiprocessor kind of architecture where one is a CPU and one is a GPU, right? Both of them are working next to each other. So both of them, when this kind of processors, now CPU is meant for different type of work and GPU is meant for different kind of work. But you cannot give, you need to give control to somebody, right? So in that case, your master is your CPU, and GPU you can say is a slave to CPU. Okay, so the master always controls the slave processor, but inside GPU, if you notice, it is a symmetric multiprocessing, right? It is all the cores are having the same having the same role. So no one is a master of anyone inside a GPU. All the cores, which is also we can refer it to as a processor, they are equal. So nobody is a master over here. So if the master fails, let's say one core is failing over here, right? So this core stops functioning. So will the other cores stop functioning? No. If the task was given to this core and this core stopped functioning, then what will happen is that same task will be shifted to some other core processor. So the same task will get shifted to other core. So nobody is a master over here inside the GPU. All the cores are same, and this is possible because of symmetric multiprocessing architecture. Right. So having said that, let me save this. So always remember when you talk about master slave processor, multiprocessor architecture, or anything, any type of architecture, usually there is one master and there are slaves. This is also applicable. This is especially applicable in distributed computing, right? So in a distributed computing, we are not only talking about threads, but we are talking about programs, right? So you have machine one in, let's say, in America, right? This is in America. Then you have another machine, let's say, in India, and there is going to be one main program, let's say, which is running in Singapore. Now, who is coordinating between these are running at different locations, and how it has been coordinated? So if machine America goes down, then what happens? If machine India goes down, so what happens? So in that case, the master is always useful, to control. And if something goes wrong, let's say this machine in America goes down, you can create another copy of the machine somewhere else. Maybe when this goes down, you are having in some other region of the world, you are having a backup copy which is, let's say, in Japan. So you can go ahead and use the Japan copy in that case. So another way which master also works is, what if the master goes down? This is a deadlock. Like if the master goes down, everything goes down, right? So how do you solve this problem? So if the master goes down over here, the master goes down, you make sure that one of the slaves become the master. So let's say when this goes down, machine India will become the master. So this is how master slave processor architecture or master slave distributed computing will always work. There is one master, but if the slave fail, then it is not so much of a problem. You can duplicate the slave on a different box, on a different machine. There are different cores. You can do n number of things, but the master is alive. But if the master dies, who is controlling it, then you make sure you either makes a slave another slave the master, or you have two masters running at the same time. So you have master 2 over here, which is already running, and let's say it is controlling uh, some other locations. So let's say it is controlling China machines, and let's say Africa machines, and Australia machines, example. In this case, the two masters are peer masters. They are talking to each other, but each master is responsible for his own zone. But if this master in Singapore something happens, master 2 over here, he will take over the responsibility for all the slaves controlled by the first master. So this is all about master slave distributed computing. So throughput computing is all about distribution, parallel computing, and getting more tasks at the same time. So another term which was highlighted was context switching. This is a very important term. So what does context switching means? If there is two instructions to be carried out, let's say but the processor is one, two instructions, one processor. So at a time a processor can execute only one instruction, and it can store the data for one instruction. So every time instruction, one of the instruction has to be allocated on the processor, and the other instruction has to be removed from the processor, and this leads to, this is a it's a kind of, your program is going to be delayed, right? If you're constantly context switching, if you context switch, like you're switching between two instructions constantly, because when it is context switching, it is not executing on the processor. That time is you lose the time for processing, and this is not a good practice. So context switching should be minimal for maximum processing. So I hope you understand this term context switching. We had spoken about this last time, and so context switching happens not only between instructions, it can happen between threads, it can happen between tasks also. It depends on how many resources we have in hand. If there are 1,000 cores, let's say, and so there are 1,000 cores in a GPU, but there are 10,000, say 1 million instructions. At a time, only 1,000 instructions can get a chance on this course, but every time that 1,000 instructions are getting executed, they have to be context switched with the next 1,000 instructions that needs to be executed. So that step of switching, from between one taking away one task away from the cores, or taking away one task from the processor and then giving it to somebody else, that time is a waste. In a way, it is not a useful time, and that is why context switching is expensive operation, and that is what we read while we were doing, right? Somewhere one of the slides said context switching. This last line, where it is, yeah, it says the efficiencies gained by eliminating, okay, you need to eliminate context switching, can be quickly eaten up by the inefficiency of the processor usage. So even if you have like a very good processor with so many cores, but if you have not programmed in a way where there is less context switching, you're not using, your program is inefficient. It is not using the maximum power of the processor. You need to reduce the context switching between the two instructions or two threads or two tasks, and you need to make sure they are independent of each other and they're not talking to each other also. So there are so many things that requires a performance of a good parallel uh, computing. So let me, so we spoke about context switching. So let me change the color maybe, and maybe increase the font. Oops. Yeah. So context switching can reduce the performance. So if you have a lot of context switching between the two tasks or two threads or two instructions, that is that parallel program is going to be inefficient. If you have dependency, dependency between two programs or two tasks or two threads or two instructions, then again the performance of because every time, let's say you're dependent, like it's like in your relay, right? When there's a race and there's a hurdle, there's that relay race where you take one fellow as a baton and the other fellow is waiting. That fellow could have run independently on his own very fast, but unless the baton is passed to him, he cannot run. So the performance of the second thread is not able to move forward because it is dependent on the first, it is dependent on that baton from that first guy. So dependency is created between two threads. If you write a program in such a way where let's say you want to calculate something like E is equal to A plus B plus C star D, okay, and you give this A plus B, you take A plus B value and you give it to one thread, and C star D you give it to another thread. If you don't get the value of C star D, how E is going to be calculated? So E is dependent on both these threads. This is a master thread and this other A plus B is a child thread and C star D would be your another child thread. So the master thread is dependent on the calculations of the C star D if it is waiting. Sometimes the child one thread may be dependent on another thread, right? So even in that case there would be a performance issue. So dependency is not good. So dependency is also means communication, okay? So communication between two instructions should not be there ideally. Communication between two threads should not be there. Communication between two tasks should not be there. So only then your parallel processing will work fast. So everybody is able to run on his own at his own pace, then a lot of tasks can be done at the same time. But if they are dependent on each other, then parallel computing will not make sense. So neither there should be, so context switching should be minimal, the communication should be minimal. Oops, which one I closed? Okay. Okay, so having said that, let's move on to presentation, the next presentation, what it is. Yeah, so part 9 basically it talks about little bit about threads. So a thread is a single flow of execution within the single process or application. So thread is nothing but a set of instructions, right? So we have said that there is a function, and here you have here you are doing A plus B, and here you are doing C plus D. So this is a set of two instructions. So you can attach a thread to this, and this thread contains the flow of execution will be this. So thread is nothing but a single flow of execution. Every application always will have one main thread. One thread can create one or more threads. As a result, the main process thread can create multiple flow of execution in the same application. Yeah, so this would mean if I have got function A, this can run on one thread, and I can have another function in the same program, which can be function B, which can run on another thread. So this can do E star F and A is equal A star C. Now here this fellow and this fellow are running on two different threads, but this fellow is dependent on the value of A and it is dependent on the value of C. If you have assigned a value of C over here, C is equal to C plus D, or let's say A is equal to A plus this, then this A plus A and C value can be very inconsistent, unpredictable and unreliable, and hence this is happening because even though you have created two threads and they are running parallelly, they are dependent on each other, and in such case you then function B has to wait till function A to get over. In that case you have to call a thread dot join function or something. So a join function is basically making sure that the all the child threads will not start until the I being a parent thread has not not finished executing. So a join makes all the child threads wait, and if the threads are waiting for some other thread to finish, then what is the use of parallel computing again, right? So the purpose of using threads is as much they can be independently executed, concurrently executed at the same time, then only it will affect the performance. So this kind of communication is not desirable. So you make sure you have your before you start your writing your parallel program, you have to plan your parallel program. You have to tell which function is going to do what, where it is going to do, how it can be parallel, is there any communication dependencies, this kind of parallel programming decisions you need to make. So each thread can be executed as per the parallel hardware architecture in place using coding techniques called coordinate with each other, mutex, critical section, resume thread and wait thread. I've already kind of given an indication of wait thread example, something like join. Okay, resume thread means even if I was supposed to let's say this thread A was has made thread B wait because of the join, but let's say thread B is waiting for long time. So how much time should we wait? We will wait for 5 seconds. After this 5 seconds I will raise an interrupt. So you can say an operating system interrupt. I'll tell the operating system that I was waiting all this time, but I cannot wait any longer. I'm going to go ahead and resume. And that is what resume means, that I was waiting so far, but now I don't wait for anybody, I just move forward. So you can write a program in such a way where you can raise an operating system interrupt, because operating system is the one who's managing the threads, right? For him, for the operating system, it doesn't matter which thread is parent thread, which thread is child thread. For operating system, all threads are equal. But if there was a communication between a parent thread and the child thread, then it has made the child thread to wait, the concurrent computing is getting affected, and hence the child thread may make a decision to say, oh no, I just want to resume. So in your exam there is going to be, this is a common question of computation, write down about computation and communication. Okay, so if there is let us take a different slide. this okay. So in your exam there is going to be a question called computation and communication. So when you talk about computation and communication problem, you're talking about parallel computing problem, you're talking about concurrent computing problem. Lesser the communication, greater the computation. I can do more if I'm independent, right? So if I am waiting on somebody else's, like in a relay race, I'm waiting for the bet and for somebody to pass on to me, and then only I can run. Then that communication is making me wait, and that is not going to improvise my computation. So lesser the communication, greater the computation. Greater the communication, lesser the computation. Uh, Lesser the context switching, greater the computation. You can do more tasks, right, if you are making sure that there is less context switching. So how can context switching be reduced, or how can you reduce the time to context switch? It is called latency time, right? Latency time means time to respond, you can say. So if your CPU is so you have a CPU and you have a RAM, right? This communication is an expensive communication. If you keep on context switching inside your RAM, this is going to be a problem, and that's why we use architecture called NUMA, right? That's what we came across. So NUMA, the processors have local memory. So they have a local memory for every processor, and there is a RAM over here. So the communication between a NUMA processor and its local memory is faster than the communication between NUMA and RAM. So the latency time is reduced over here. So this is lesser latency time is equal to greater computation. Greater computation is equal to greater throughput. Okay, so remember that if there's a question on computation and communication, all this matters. What is the latency time? How much of context switching is happening? How much of dependency is there between the two tasks that is being performed? What is the communication level happening? How complex it is? You have to keep things simple, So and only then you can achieve the maximum computation and maximum parallel computing, and greater the computation, better the performance. So what is mutex and critical section? If you have done threading, so I'm going to teach you a little bit. So then let's say there's a thread 1 and there is a thread 2, and they are dependent on each other. So how will thread 2 know when it is okay to move forward, or when thread 1 will know that when it is okay to move forward? So what they do, since both the threads, if both the threads are running in the same process, they are part of the same process, they are child threads, that means they are sharing the memory also, right? So in the memory, I'm going to use a variable called a Boolean variable. Let's say it's called mutex is equal to true. If this mutex variable is true, then thread 2 will start. If mutex variable is false, then thread 2 will continue. So we are dependent on this mutex variable. Mutually exclusive, only one thread can run at a time. So mutex stands for mutually exclusive. So this is a multi-threading technique actually. Okay, so and what is critical section? So let's say we have thread 1 and we have thread 2. They're both running parallelly very fine, right? But at one point this thread 1 calls a shared function. Okay, which does something common, like let's say, and at the same time this thread also runs parallelly fine, but at one point this fellow also calls the shared function. Now if both of them are executing the shared function, and here you have said let's say a is equal to c, let's say, and you're passing c as an input parameter over here inside the inside your function as an input parameter. So this fellow is also giving you c, and this fellow is also giving you c. So what will be the value of a, which value of a, which will be which c, which will be the c given by thread 1 or thread 2. So this is leading to synchronization issue. So the threads have to be synchronized, they're dependent on each other. Dependency is not good, but sometimes you have to synchronize the thread. Both of them cannot update the C at the same time. No, then you're confused, and which C is the correct C. So either you make one thread, this function, you lock it basically. And when you lock it, what you're trying to say is, you're trying to say if you lock this function is synchronized. If this function is synchronized, and what you're also trying to say that this is a critical section. That is what critical section means. It means it is a shared code. So which means that when thread 1 has entered in first, thread 1 got a chance first, he entered in, he modified the value of C. Then he will get to modify, and that value will be updated to A over here. So if thread 2 is reading the value of A over here, now thread 2 has a chance to enter to read the value of A, which was updated by thread 1. So thread 2, and once thread 1 is out of this block, here it enters the block, and then here it gets out. So at a time, how many threads can run in one critical section? Only one thread. Can access and share the code of the critical section. So these are all if you're writing a multi-threading programming, or if you're working anywhere where multi-threading has been used, you're going to see all these critical sections, synchronization, locks, mutexes. So you have to know the concepts of threads for this in order to understand a thread program, and even write a parallel program. So greater the synchronization, lesser the computation. So it's all connected, right? Because synchronization, you're making the function, that function is making the threads wait, right, before it enters, and the moment you make it wait, definitely it will affect the computation. So synchronization is also a reflection of greater communication. So that is what, again, there's a point of computation and communication. So computation is more when the communication is less. I can do more when we talk less, something like that. Okay, this is saved and the same. So the by default operating system is very intelligent how to break everything into threads. So most of the time, even though your program is not multi-threaded, operating system will break down your program into multiple threads and run it for efficiency purpose. So that is what it means, implicit threading. Implicit threading is something that is done by the operating system itself, or done by the processor itself. You don't have to tell the processor how to distribute the task, how to distribute, how to multi-thread. It will take care. It is intelligent to know which can what functions are dependent, not dependent. All the decisions are taken at the operating system level and by the processors. Explicit thread is when as a programmer you intentionally create threads for your performance. You are taking the ownership of parallel programming. So your multiple threads can be used, like one thread can be used to access your hard disk, one thread can be used to access your internet, one thread can be used to run your Java program, right? So your threads inside your computer, a lot of things are running. So definitely multi-threading is used over there by the operating system heavily. Parallel architecture enables throughput computing. Now this is obvious, right? Because there are parallel architectures, you can do more tasks, and more tasks means more throughput computing. So this is thread is a single control flow, which is a logical sequence of instructions. We have already done this. We have already spoken about interleaving of the task, which is multitasking, and context switching. So here it gives you an example. There is a shared memory on the top. So there is a shared memory on the top. So this program starts, the main thread starts, and it has its own local storage. It will have its own local storage, means so its own local variables, and there's its own instructions. So at this point it creates another thread, and this fellow thread 2 starts parallelly over here now. And at this point thread 2 starts, and this starts parallelly, and thread 2 starts thread 3 over here. So one thread is starting another thread over here, but all are sharing a shared memory. Each thread will have its own thread local storage, means it will have its own local variables. POSIX is basically a standard defined for Unix operating systems. So because you have so many Unix flavors, right? You have Ubuntu, you have Red Hat Linux. What is the difference? What is common between them? So POSIX is a common standard. So if you're implementing a Unix operating system, then you have to follow POSIX. And so POSIX also one of the standard that it defines is how to write threads. So every thread is have these attributes. I for instruction. Every thread will have a certain set of instructions to be executed. Every thread is mapped to some function. Either it is a main function. If it is a main function, then it is a parent thread. If it is a local function within your program, then it is a child thread. So but it is going to be mapped to some function. So every thread has to be initiated. That thread can be created, terminated, or joined. So I already explained what joining means, right? You are creating a dependencies between the two threads where you're making the other threads wait till the parent thread is not completed execution. And what is a state? A state is basically, we mentioned this in the last lecture again. State is nothing but a set of variables, or the set of your state is like your cricket score, right? Which over the state of the cricket match changes, which means the score is changing. So thread also has a state. Every time you move forward with the instruction, the state is also changing. A thread has a state that determines its current condition, whether it is executing, stopped, terminated, and waiting for I/O. A thread has actors. The sequence of states that a thread undergoes is partly determined by the operating system scheduler actor and partly by the application developer's actors. So thread, even though it is independent, it is sometimes also dependent on the other threads, on the other programs, right? So those are called actors in the same system. Thread has a memory, shares the memory of the process, and since they execute it concurrently, they need synchronization structure. What is the synchronization structure? We spoke about mutex and critical sections. And I'm not able to read the last part. What it says, synchronization, different synchronization abstractions are provided to solve different synchronization problems. So you understand now what synchronization means, right? Synchronization is basically you're coordinating between the two different threads. You're making sure your program is running as it is required, right? So you cannot, let's say if you are putting something on a gas, first you burn the stove and then you put the vessel on the stove. So these two operations are sequential. They cannot be executed parallelly, right? So if you go parallelly, then it can be a problem. So there needs to be a synchronization between some threads. So in C there is a header file called pthread.h which is used for threading, and even Java and .NET has its own threading classes. And inside a virtual machine, if you're running the thread, those threads are called logical threads. Okay, so what that means is, see, ultimately the instructions are run on the hardware, right? A virtual machine is not a physical machine. It is just like if a virtual machine, inside the virtual machine you're saying create two threads, where it is going to run? Is it have its own processor? No, the virtual machine is installed, let's say, over the operating system. Now for the operating system, the virtual machine is one thread over here. Internally in that one thread, virtual machine has created two threads now. When operating system is managing all the threads, right? All the threads are over here in your it is shuffling between your memory and processor. How does these threads get translated into physical threads? So this is actually called the physical thread, the one which is run by the operating system. So these threads are called logical or managed threads. These are not real threads, but you have created it within the virtual machine. The managed threads, ultimately, unless and until it has been converted into physical threads, it will not make sense. If two logical threads are not converted to two physical threads, then what is the use, right? So that kind of decision is done by whoever is controlling. Either it is an operating system or either it is a hypervisor. Somebody, the intermediator, whoever is managing the virtual machine will decide how many physical threads has to map to the number of logical managed threads, because the hypervisor or the operating system must be managing multiple virtual machines, right? So should we give preference to only one virtual machine, or should we give preference to equally to all virtual machines? What is the kind of decisions you're going to make? Those are the kind of synchronization, which scheduling and synchronization happens at the operating system level and hypervisor. So every thread will have a start state. When it starts, it goes in the start state. When you stop the thread, it goes in the stop. Stop is something like wait, and join is like you're blocking the child threads till all the parent threads are not completed. And then you have a suspend state. So suspend state is like your wait stage, halts the thread execution indefinitely until it is explicitly resumed. And I've already spoken about resume, right? You raise an interrupt and you start resuming it. So there is only two possible ways to resume. One, all your dependent threads have finished executing and now you can resume. Or second scenario is when your dependent threads have not stopped and they're still running, but you raise an interrupt and you resume yourself. And abort is basically you're getting out of the memory and removing the thread out. So sleep is basically a waiting for a certain amount of time. So you're saying before I will wait for 5 seconds. So that is like saying I'm sleeping for 5 seconds, and once after 5 seconds I will raise an interrupt and resume myself. So that was So parallel programming techniques in concurrent computing. So developing parallel application requires you to understand the problem and its logical structure. If you're writing parallel application, you have to know what type of problem you're solving and whether you can make it parallel, right? Some things cannot be made parallel if there is a dependency. If there is too much of dependency, it is difficult to make it parallel. There's no sense in making it parallel. So one way of doing parallel is what technique we have discussed, this technique called decomposition, right? Breaking down the task or breaking down the set of functions. So decomposition is a useful technique that aids in understanding whether a problem is divided into components that can be executed concurrently. So there are two types of decomposition. One is called the domain decomposition and one is called the functional decomposition. So we'll look at that now. So one is called the domain decomposition. It basically, you're trying to tell you're trying to decide what type of problem it is. That will depend based on the type of problem. You can either decompose functionally or using the domain. So what is domain decomposition? Domain decomposition is so let's say you have a very huge big data, right? You have a huge set of data. So there is data 1 over here, data 12 over here, data 13 over here, and data 20 over here, and this is like millions of data is so this goes on and on. This is a big data, there's a huge data. So and each of this data, you simply you want to run one instruction or one program. So you have a one instruction or one task or one program, right? Whatever it is, the instruction is common, the task is common, or maybe it is just one function. So in this case, the data is huge, but the computation is small. Or maybe you can say computation is repetitive. So your whatever data comes in, first time you're operating on one, second time you're running the same instruction. So the instruction can be add, or maybe you're calculating the log of 1, you're calculating the square root of the number. You may be doing any number of things, but you are doing the same set of instructions or the same function on each of these elements. Now if you take a sequential approach in this case, this is going to take a lot of time, right? If there's 1 million data, then you're making a sequential approach, so it doesn't make sense. The computation is repetitive and it is called embarrassingly parallel. How much parallel you can get? This is the height of parallelism, where every data is running through the same instruction. This is a classic case of parallel problem, which you can simply solve it using parallel problem, right? How? By breaking down your data sets into multiple data sets over here, and then trying to create different threads to run the same instruction. So this will run on thread 1 or core 1. So this can be on thread 1 or core 1. Core is your processor, okay? Or this can be even your computer 1. Or this can also mean your slave 1. This can also so remember this, a master slave model, where you can have any number of slaves. You can create any number of slaves. You can have any number of computers doing a parallel computing. You can have any number of cores doing a parallel computing. You can have any number of threads doing a concurrent computing. At every level there is some level of concurrency which is happening. So this fellow will be running on thread 2. or whatever, the core 2 or something. Now why it is called embarrassingly parallel? It is called embarrassingly parallel because they are not dependent. There is no dependency between parallel operations, right? If you're calculating the square root of each number, the square root of 12 is not dependent on square root of 1. So there is no dependency. There is no dependency. There is no communication between the two different parallel operations. This is an embarrassingly parallel problem, and this type of problems are called domain decomposition problems. Okay. So that is what domain decomposition. Your parallel computing is best suited for domain decomposition problems. So then the question is, what is functional decomposition, right? So let us so in your functional decomposition, it is actually the opposite. So you have so you have a program where you have to calculate a sine function. Let's say you have to calculate the cosine function on the same value. You have to calculate the tangent value x, and you have to calculate the square root of x, and this can go on and on. So what is common in this is the value of x. So the data is not huge, but the computations that needs to be done on x is different. One time you have to calculate sine function, right? And the other time you have to calculate cosine function. The other time you have to calculate tan function, and the other time you have to calculate square root function. And all of this, let's say, is in calculate function, calculate x. All this task is done in the same function. Now is this an embarrassingly parallel problem? No, this all this how can you break this down? You can only break this down by running this on one thread, running cosine on another thread, running tan on third thread, running square root on fourth thread. This is the only way to do it. In this case also the dependency is low because the cosine function is not dependent on the sine function calculation. The tan function calculation is not dependent on the other calculations. So the dependency is low, the communication between the threads is low, and hence the performance will be also good. But this kind of problems are not embarrassingly parallel problem. This is basically you're decomposing based on functionality. So that is what functional decomposition is. And what is domain decomposition? Domain decomposition is decomposition based on data. So that is how your big data problems are solved, right? You break it down into different data sets and you distribute it each data set to each slave, each computer or each code, and they will do the operation. So each one of them are running on a different thread over here. This is running on thread 1. And this fellow is running on thread 2. And you can create any number of threads. But this type of problem is called functional decomposition. But at the end, you need to get all these threads together, right? Over here. So you need to sum this value in the end. Let's say in the end you have to do a sum of sine, cos and tan. sum of sine x plus cosine x plus tan x plus square root x. But even though the sum function is dependent on sine cos tan, the sine cos tan are independent and they can be executed faster and they can be summed up over here. So this is what is called functional decomposition, where decomposition is done not based on data. In this case, the data is just same data which has been applied on different functions. So you have to understand the nature of your parallel problem. Is it a functional decomposition problem? Is it a domain decomposition problem? Is it a mix of both? And if you have to write a parallel program, how you should construct it? The best way to construct is you can make it functionally decomposable, and the main thing it is that you should reduce the communication between two functions or two data. Whatever way you're decomposing, the communication between the two threads or two operations should be reduced for faster efficiency and performance. So it says domain decomposition is a process of identifying pattern of functionally repetitive but independent computation on data. Domain decomposition is a most common type of decomposition. You are looking at embarrassingly parallel problem. What is an embarrassingly parallel problem? An embarrassingly parallel program has these three attributes. The calculations are identical for each and every operation. They only differ by data that they operate on, and they can be executed in any order. Okay, as far as any order is concerned, it means it doesn't matter whether so let's say in this case we can also speak about that. So you have 1, you have 12, you have 20, and you have to do you got the data in this order. But does it matter whether you calculate 20 first, or whether you calculate 1 first or 12 first? No, you only have to divide your data sets. In what order the operating system or processor executes, it doesn't matter. Yeah, maybe 20 is calculated first, that is fine. And so embarrassingly parallel program can be operations which can be executed in any order. Then only the problem is said to be embarrassingly parallel problem. Embarrassingly parallel problems constitute the easiest way of parallelization because there is no need to synchronize between different threads that do not share any data. Right? We have already went through this. And here we are looking at the master-slave model, where one code segment contains the decomposition, coordination logic, and another code segment contains a repetitive computation. So when there is a problem coming in, been given, let's say the problem is given to the function, or so there is going to be one master function or one master. Either this can be a function, or either this can be a processor, either this can be a computer, right? Somebody is a master. He actually it's not he or she, but whatever it can divide. The master can decide how to divide, how to decompose these problems, and how to distribute it between different slaves, right? So so you can have node 1, let's say computer 1 over here, or processor 1, or core 1, or different functions, like so we had to make a summation of sine, cos, tan and square root in the earlier problem. You can distribute it that. So your distribution task is called, you can say it is like your mapping function. But at the end, all this data from different nodes, they have to be collected, summarized and summed up or do something and given back to the master also. So this kind of functionality is called reduction functionality. So one is decomposing, and the other one is aggregating it. Like it is taking the sum of whatever was decomposed. So one fellow is, the mapping function is dividing into different tasks or different functions or different threads and assigning it to different cores or different computers. And what is reduction doing? Reduction is doing the reverse. It takes the value input from everybody inwards and it gives the value out. So this fellow, the mapping function breaks down the single, breaks down your single task or your single function, or your it breaks down into multiple parallel components. Your reduction or your reduce function is collating all the different related threads together or related functions together, all the related parallel components together and giving back the value. And this is the concept which is even used in map reduce architectures. So this is also one of your assignment, right? Your Hadoop is based on map reduce architecture. So then we have thread pooling. So what is thread pooling? So let's say you have a machine, right? You have a processor and you have a RAM. Now whenever any process starts, what let's say there's an operating system over here. So whenever any process starts, it's like we have to create the thread, right? Create the thread. So it is same as start the thread, right? These are the operations: start the thread, stop the thread if need be, resume the thread, then terminate the thread. The thread can be in different states at any given time, and there can be but how many threads you can create in one memory? Memory space is limited, right? There is only certain number of threads you can create. So in that case, the operating system is very intelligent. So, and what it does, it says if anybody wants a thread, I will create a pool of threads which is so there is, let's say there's a thread pool over here. So it is like your swimming pool, okay? Let's say, for example. So this is like your thread pool. So the threads in the thread pool, they will be ready waiting over here. 1, 2, 3, 4, 5. And anybody who wants to use this thread, they can use it over here. And so process 1 wants one of the threads from the thread pool. It will get it. Now, is this thread in a start state? Yes, this thread, the threads in the thread pool is always ready to go. It is so the time is reduced to initialize a thread. You don't have to run through a lot of processes when the threads are already available in the memory. but you can always only get certain number of threads from the thread pool. There may be only 1,000 threads given to you by operating system or by your Java runtime, so that your RAM does not get full with unnecessary number of threads. When process 2 is over, process 2 will remove this, say I don't no longer need the thread, and the thread can go back to the pool for some other process. So some other process then can get access to the same thread in the pool, but in this case the data and the code that needs to be executed is going to be different. Okay, so you can get the same thread. So there is some bit of thread performance optimization happening because of this. You are making sure your RAM does not get clogged with unnecessary number of threads, and it is managed in a controlled manner. So that is what is called thread pool. So Java usually has its own thread pool. It will not allow you to create physical threads. It will have a thread pool of certain number of physical threads, and only that many threads it will keep on rotating between different clients. So what is inherently sequential problem? It says if the values of all the iterations are dependent on some of the values obtained in previous iterations, then it is said to be inherently sequential problem. So this is also talking about data dependencies. So let's say a value of 1 is here, I pass, value of 12 is given here, and value of 20 is given here. Now what it's trying to say, before you calculate 20, before you operate on this 20 data, you need to finish operation on number 1, this data. Means only if operation on data 1 is done, you can start your operation on data number 20. So this kind of problem is not an embarrassingly parallel problem at all. This is a inherently sequential problem where even though the data can operate parallelly and separately, it is still dependent on some other data to be operated before it can proceed forward. So when this kind of problem statements comes, it is difficult for the operating system or the processor to go ahead and make it run parallelly. It is difficult even for the developer to write go ahead and write a parallel program. So inherent sequential problem increases communication and reduces computation. So this is your functional decomposition, where you are dividing in the number of work, units of work. So unit 1 is function 1, unit 2 is like your cos function, unit 3 is like your tan function, unit 4 is like your square root function. So you are dividing your single process into units of work and assigning it on different threads, and at the end, so this process where the process is breaking down into number of units is called the mapping function, and this process where you are taking all the units and core and combining it into one result, it is called the reduction function. So we have already spoken about computation versus communication. In designing parallel and in general distributed application, it is very important to carefully evaluate the communication patterns among the components that have been identified during problem decomposition. The two decomposition methods presented in this section and the corresponding sample applications are based on the assumption that the computations are independent. So the decomposition techniques assume that computations are independent of each other, which means the input values required by one computation does not depend on the output values generated by another computation. The second thing is the computation do not interact with each other. Not only they are independent, which means they are not an inherently sequential problem, and computations do not interact with each other. They don't have to, like, you don't even though they are not dependent on each other, don't increase the number of communication between the two. because then you're creating a complex program, right? If all the people in the room talk at the same time, how will anyone understand what is happening? We cannot. So that is what, the number of interactions also leads to complicate a complicated program. So make sure whatever problem statements you have, if you're making it parallel, make sure they are independent and they are not interacting with each other, they're not passing data to each other. So so when you come across MPI, a message passing interface, it is all about passing data between two different components inside, running in the system. And so that, though that is not recommended, sometimes it is necessary, because not all type of problems can be made parallel. Some are going to be sequential, some are going to be having independent dependency with each other, and some are going to be having interactions with each other. So embarrassingly, parallel problem, domain decomposition problem is very well suited for parallel applications, but you cannot assume that all type of problems are of that nature. The two assumptions strongly simplify the simple. So two assumption is this, right? The computations are independent of each other and the computation do not interact with each other. The two assumptions strongly simplify the implementation and allow achieving high degree of parallelism and high throughput. So it is directly connected to how much parallelism you can achieve and how much throughput you can achieve. Having all the worker threads independent from each other gives the maximum freedom to the operating system or the virtual runtime environment scheduler in scheduling all the threads. The need to exchange data among different threads introduces dependencies among them and ultimately can result in introducing performance bottlenecks. So if one is dependent on the other, then it is a bottleneck problem. You're dependent on that, and the two threads cannot perform, and hence it will impact your performance of the machine itself, or problem of the performance of machine or performance of the function. And this says the need for synchronization between threads can lead to low throughput computing and defeat the purpose of parallelism. So we have already spoke about how synchronization leads to a weaker performance of a parallel problem. The lack of communication among different threads constitutes the condition leading to highest throughput. So lesser the communication, higher the throughput. So that is was for concurrent computing. So are you able to hear me? Or I just want to make sure you are too silent. Hello. Okay, great, thank you. So now we'll go through some demo maybe. Let's see, I need to. So these are actually assignments also. So this is assignment 1. Okay. So there are 3 programs in this. One is an example of wait, one is an example of join, and one is an example of fork. Fork is basically creating a thread, okay? Creating a child thread. So let us see if we can look at the code first. So we have a thread fork example over here. So it is using this classes java util.concurrent. Right, and then this is a loop over here where it is using threads. Hold on. T1 and T2 is used to calculate the time taken via sequential approach and parallel approach. Okay, so there are two approaches been utilized over here. Oh, this is the so the top code is sequential and the down code is your parallel programming. See, it is saying fork join pool, and it is telling how many threads you should create, and it is passing um, different data to it. So all the computation is done. So this is something y'all will have to go in detail in the program. I cannot explain everything. Y'all have to see how the program is written, how the parallel programming is done, but let's see if we can run it quickly over here. Running is the simplest thing, but explaining this is is going to be take some time for you to understand the program. So it says sum of all numbers using stream in Java was 499500. Achha, this is the summation of all numbers. So there were a lot of numbers been passed as in the function, and then Java stream technique time taken is 54 milliseconds. Sum of all numbers using sequential loop in Java. So this is a sequential technique. They have used the additions. Java for loop technique time taken is equal to 13 milliseconds. Total available processes is 8. These are the logical processes. I've got a quad core, and each core is hyper threaded with is running two threads on the same core. So that's why it is 4 into 2 is equal to 8. The sum of all numbers using parallel computing forking technique is 49500. Parallel computing using forking technique time taken is 24. I don't know what it seems like. This is a milliseconds to me. Okay, so do study this program. The parallel program seems to be taking the sequential technique seems to be taking 54 milliseconds over here. It's given over here, and this is 24. So I do not know what exactly this 13 is. It seems to be some sequential thing going on inside the loop itself. So have a look at that. But one is 54 and one is 24. Using the sequential technique, it's taking 54 milliseconds, and using the parallel technique, forking technique, it is creating multiple threads and using the maximum power of the processor and distributing the number of instructions. It is 24. So there are three programs over here. This gives you an example of thread wait example, thread join example. So have a look at it. What is this? This is your parallel stream. Okay. there's a program inside the main. Okay, so parallel stream. So it is creating a list of objects which is employee type OEM and doing something, and then it is calculating the sequential approach time taken. Then it is coming here and it is using this function elist dot parallel stream. This is a so it is dividing your data and where is for loop? So it's taking a list of all the employees and it is dividing the, it has to calculate basically the salary for each employee, and so it takes every employee and filters it out and divides it into parallel stream. Parallel stream is nothing but dividing your data into multiple sets and then executing it at the same time. So this is a domain decomposition happening over here on this line of code. So let's run this program. Oh, did I close? Okay. It is doing something. This is a parallel. It's processing a lot of employees. Okay, that is what it is doing. So it says parallel stream count. So there were 300 employees, and parallel stream time taken is 11929, assuming that is maybe milliseconds. Oops, error. Okay, no problem. But I'm just looking for the sequential time. Do we have that data? So sequential time took 12703, right? And parallel program took how much did the parallel program time take? It took just a little less, 11924. So I think I seen this problem. Let me see. This is happening because I think of this line. You're writing a system.out over here. So while you're calculating the employee's salary, you're trying to write something to the screen, which is an input output operation. So this input operation output operation is like you're talking between the memory and your screen, right? Your screen is your output screen. So if you're going to have an instruction which is of input output time while you're doing your calculation, that is going to add a lot of time. So I've commented this code and let us see the difference now. Like, does it make a difference? So this fellow employee saved, right? So I'll have to compile again. So remember, one was like 11,000 milliseconds and another one was 12,000 milliseconds, just a 1,000 milliseconds difference. It is like only a difference of 1 second between sequential approach versus parallel approach. So I have commented the code which is doing input output operation over here. So I don't, whenever I have to get a salary, I have to just return the salary. I don't want to do print it on the screen. Printing on the screen is an expensive operation. I'm compiling. Hopefully it will compile, and now I'm going to run the program. Okay, so I've commented that output, right? It was constantly commenting. So now it has taken, time taken is 24 milliseconds, and this fellow has taken 20, and that is a different error, something with open JDK. So we don't have to worry about that. Sorry, sequential stream time taken is 24 and parallel stream time taken is 20. So suddenly we have reduced from 12,000 to 24 over here, and this fellow is reduced from 11,000 to 20 over here. So there is a difference of 4 milliseconds between sequential and parallel. So remember, I have a quad core inside my box. So even though if I am not writing a parallel program, it is going to be parallelly done by the operating system. But here I have done a kind of an implicit parallel programming inside my parallel stream demo using the parallel stream function of the Java. And then there is another decomposition problem. This is a Visual Studio. Oh, I've already opened. So this is your functional decomposition problem, and so here you have a class called sign, and in that sign function, in the sign class, you are doing you're basically calculating the values, right? You're calculating the sign function, you're passing in double x, and then you're returning the result to update result updater, which is like your reduction function over here. So sign, so every time somebody is calculating something, it returns back to this common function, which will ultimately reduce all the, like, aggregate all the data and give it back. So then you have a cosine class over here, right? Another class which is which the purpose of this class is to calculate the cosine value. So you see there's a cosine function over here, and this is the function being called to do the cosine operation, math.cos. So once it is done, it kinds of calls this reduction function, which is running independently. So there's a tangent function also in the same way, and this is where your main function starts. This is where your program will start. So how does your main program starts? It initializes, it says x is equal to 3.4, and then it says sign is equal to new sign, and thread t sign is equal to new thread start sign dot apply. So basically you're starting a new child thread over here, which is going to calculate your sign function, and then there is a new thread which starts over here, which is going to calculate your cosine function, so second child thread. And here there is a third thread which is going to be started. So it starts your tangent function, start thread, sine function, and cosine function. And what happens in the end? They are joining, right? They are waiting on the parent thread has to make sure everything is executed on the top, and then finally it comes and it writes program.result. Program.result is basically the reduction function is this function is called. If you look at the program, you can this function is called ultimately by the each of this sine function, cosine, and whatever value they calculate is given over here, and it basically adds it to the result. And if you notice, this is a synchronized code. It is locked, which means only one thread can update this section of the code. It is a critical section code which is going to be executed only by one thread at a time. So can we run this program from here? So this is a functional decomposition problem. Okay, what happened? Oh, I think it finished execution, and Can I run it from command prompt? So yeah, the ex is created here. So let me run this. So what is the name of the exe? Functional decomposition example. So here you see tan has been calculated, cos has been calculated on a separate thread. There are three. What happened? There were three threads created: tan thread, cos thread, and sine thread. In the end, the reduction function, which was a sum, it took the value from all these three threads and created a sum value over here. It added all this tan, cos, and sine and give you the final value. So this was again, I have not printed the time taken, but definitely this was done using multi-threading, which was a functional decomposition example. So with that, we can I'll take the attendance now and we are done. Is there any other question? Okay, so let me take the attendance. Okay. Deepesh, Durgesh, Goody, Isha, Joel, Irfan. So in your demonstration, you need to explain, okay, study the program properly and explain how things are working, what is happening at each step, and just running the program won't be enough. So you don't have to write the program has been given to you, but you have to explain the program and run the program. But as you noticed, these are the simple ones, right? Because it executes on your machine. There's no much hardware dependencies. Rishabh, Rushali, Sandhya. So when you are trying to divide your assignments, try to evaluate the strength of your team. There may be some teams which may be technically weak. If they are, then give them the simple task, which is the lower difficulty level. And if you're a little technically, you can carry off difficulty level. If a task with a greater difficulty level, do that, because that is also going to give you more experience. More the difficulty, more better the experience. Okay, so I have taken today is November, so will be uh, so for today we are kind of done. Is there any other question? Let me stop the recording.